we looked at the notion of, so we had this notion of measurability, uh, independent of a background measure. Of a background measure. So this leads us to talk about almost everywhere. We had G, which is the notion of a rough Riemannian metric, which means basically that G and G inverse are in L infinity lock. That's another way to think about it. So these are matrix valued, well, locally matrix valued, almost everywhere symmetric functions which are in L where they're G and G inverse, by which I mean the inverse of the coefficients in any chart. These are in L infinity lock. And we saw that in general, C infinity C, we showed that R2 is not contained in the domain of D star of G. And I just want to say something with regards to this. So we had this discussion right towards the end where we asked, well, you know, if we do have it, then does that mean that the metric is smooth? Unfortunately, you know, it's late at night for me and I'm running on one cylinder, so I couldn't give you a very satisfactory answer. But the bottom line is no. And the reason for that is that we could immediately see that this is equal to, well, B inverse D star, which is the Euclidean one, B, right? In this situation. So these coefficients are typically L infinity. So we need to really make sense of this in a reasonable way. At least in the example that I wrote down, they are in L infinity. But of course, we can see that if the metric was, say, C1, then certainly B would map smooth, compactly supported sections, these are sections, to once differentiable sections. And D star can still act on that. In fact, the metric G here can even be Sobolev and say W12, and that's enough to guarantee that that compactly supported sections are in the domain. Okay, so just a little caveat. But what I really want to say is that this complicates things. So then the question of forming this operator dg, which is, you know, d plus d star of g with domain d intersect, well, domain of dg with being the intersection domain, dom d star of g. I mean, this could be 0, right? So that's a big question mark. I mean, it could be really bad. So we can't even really talk about, this might not be a densely defined operator, certainly not self-adjoint, etc. So this is the complication. This is the complication in low regularity. So we have to rectify that first. We have to at least be able to make sense of the question, right? If we want to say something about the kernel of dg being isomorphic to the singular cohomology, I mean, even before we get to any of this stuff, we have to be able to make sense of this operator as a reasonable operator. So this example shows that, you know, we're in murky waters, and this is a difficult problem. Okay, so where are we? So what I want to say, I've rectified some of my technical issues also. So what I want to really do today is to show you some abstract techniques, functional analytic techniques that allow us to overcome this, right? So Hilbert space Hodge theory. Okay, so that's really what I want to introduce to you. So so this I learned. So this is nothing new that I'm telling you here. So this is stuff that's known. I used some of this in my PhD thesis, in fact, many years ago, in 12 years ago. And this was originally due to Axelson, who's now known as Rosen. Okay, so he's my academic older brother, and McIntosh, who was my supervisor, and later also Stephen Keith. Okay, so let's fix some notation here. So I want H. This is just a separable Hilbert space. Okay. And I'm going to assume complex, right? So complex Hilbert space. I like everything to be complex. So the inner product is conjugate linear. Okay, so if we're in the real setting, also we just complexify and move on. Okay, and I just want to recall some basic notions. So I want to talk about an unbounded operator, which maps from some subspace of H to H. So this is so when I say operator here, I always mean linear. Okay, so for me, operators are linear. I'm a linear boy. And so this is called a closed operator if the graph of this, which is in H cross H, is closed. And of course this means that if UN converges to U with this in DOM gamma, and gamma of V UN converges to some V, then that means that U is in the domain of gamma and V is equal to gamma of U. Okay. So these are, of course, almost continuous, meaning that if we have a closed operator and the domain is the entire Hilbert space, then it is a bounded operator. It's a continuous operator. Okay, so I won't get too much into that. The important thing is that if this is dense, then there exists a unique adjoint given by with domain, with the domain we can specify. Okay, the domain is exactly going to be the V in H such that gamma of UV is less than or equal to some constant. The constant may depend on V, norm of U. Okay, so of course this tells us that by the Riese representation theorem there exists some F so that this can be written as Fu of V. Okay, and the F then would be gamma star. We can write this as U, comma F, and the F would be the gamma star of V. Okay, and this satisfies U gamma UV. Gamma UV is equal to U gamma star V on respective domains. So again, I just want to really emphasize that and gamma star is closed. Okay, so if this is densely defined, this is closed. If this is both closed and densely defined, then this is also densely defined and closed. Okay, so gamma closed and densely defined implies if and only if gamma star, implies, not if and only if, closed and densely defined. Okay. All right. So I just want to recall some of these facts. And for us and throughout, we want to talk about an operator being nilpotent because this fits with the specifics, the geometric specifics that we want to apply this to. Okay, so I want to give a definition here that gamma is nilpotent for us, or 2 nilpotent. If you're really an algebraist, I guess it's 2 nilpotent if the range is contained in the kernel. Okay, so if we have a closed if gamma is closed, then of course we can put a closure on the range, because the kernel of a closed operator will be a closed subset. Okay, so so that's something to bear in mind. So I'll write that as a remark. Closed and nilpotent implies that the range of this is contained in the kernel. That just follows from the fact that the kernel is closed. Now let me say something. So lemma, if gamma is closed, densely defined, and nilpotent, then gamma star is also closed, densely defined, and nilpotent. Okay, so the proof of this is just a calculation. Okay, so calculate using duality. If you use duality and you calculate, you get it straight away. So from here on, the background assumption is that this is a closed, densely defined, and nilpotent operator. Okay, so I want to just really fix that in the background so I don't have to keep writing it again and again. And now, following the sort of the framework that we have of the situation in with say d plus d star, what I want to do is I want to define a Dirac type operator now. So I want to define pi as gamma plus gamma star, with domain of this pi being the domain of gamma intersect domain of gamma star. So the problem still persists that this could be empty. Okay, well, not empty, but zero. These are vector subspaces. It'd be bad if it's empty. So so generally the sum of operators is not well behaved, or unbounded operators. If they're bounded, of course, there's nothing to do. But in general, the sum of closed operators are bad. Okay, they behave badly. So so generally we may have that the domain of pi is 0. But you're all here now, and I don't want to spoil the surprises, but you may have already guessed that this is not actually the case. And what's really remarkable is that it's just a nilpotency. It's just this algebraic condition that is so rich in analytical structure, it's mind-boggling to me. Every time, I mean, I see it, but you know, as Cantor said, I don't sometimes believe it, because so much follows from nilpotency. And that's something I really want to emphasize here. So so let's do it. Let's have a look. So let me give you a proposition here. So before we talk about the nice properties of this, it could be that this domain is 0. But I want to just point out a few things. So for all u in dom pi, we have this nice splitting. We have that the norm of pi u is comparable, right? So whenever I write this here, it means that there's a constant that bounds it above and below, okay? Gamma u plus gamma star of u, okay? That's the first thing. The second thing is that the kernel of this pi is the kernel of the intersection of the two, which might not be a surprise. And the third thing is that this is closed. Okay, it could be a closed operator which is not densely defined. It could be a closed operator with domain that's 0. Okay, So I'm just going to very, very quickly show you how to argue this. So if I fix u in the domain of this pi, at least one, let me at least prove you one. So clearly we have that pi of u is going to be less than or equal to gamma of u. That is just a triangle inequality, okay? Because it's the sum of the two operators, and the domain is the intersection domain, so each of these operators can act on it, so nothing really to see or do here. But let's try and go back the other way. So let me take this u and let me just expand out to you gamma of u. Okay, so gamma of u here is equal to something stupid. I'm going to do something completely stupid. I'm going to add, remember, the adjoint is nilpotent. So I'm just going to add the square power. So of course the range is contained in the kernel, which is contained in the domain. So again, everything matches up here. And now I'm going to expand this as an inner product. And then I'm going to pull one power across. So this is going to now be gamma star of u, gamma of u. Okay, that's what I get in the end. And what do I do with this? Well, I combine these two. So I have a common factor. So this is not a pi, this is a gamma, right? So I combine this together. So I get gamma of u plus gamma star of u. So that's pi of u, right? So let me write pi of u. This is pi of u, gamma of u. And of course everything is this is a real number here, so this is now going to be less than pi of u, gamma of u. Okay? So if I divide through now by this, I conclude that gamma of u is less than pi of u. And interchanging the role of gamma and pi, I'm going to get that gamma of u plus gamma star. Sorry, if I interchange the role of gamma and gamma star, I get the exact same thing, right? I do this exact computation with gamma star. This is going to be 2 pi of u. So actually, I can even really quantify this constant here. So the rest, 2 and 3, I'll just leave it as an exercise. It's nice to try your hand at this if you're interested in this stuff. But it follows more or less from the same reasoning. Okay, great. Now I want to show you maybe, very early on, right into the early part of all of this, I want to now show you something quite exciting. I want to show you the Hodge theorem, right? So what I want to prove is this. What I want to prove is that the Hilbert space now splits into the kernel of gamma intersect the kernel of gamma star plus the closure of the range of gamma plus the closure of the range of gamma star. Okay? This is what we want to prove. But before I prove this, I want to present to you a lemma on projections and on splittings. Okay? And I want to emphasize that in what is to follow, these splittings won't necessarily be orthogonal splittings. So when I'm talking about splitting a space, I really mean that I have a projector in the sense of a Banach space projector. So an idempotent that is bounded. Okay? So let me lift all of this just to kind of really be clear about the language. Let me say that I have B, which is a Banach space with a norm, right? This is my norm. And when I say that B is equal to B1 plus B2, I mean, here we have no notion of orthogonality, right? So we're really forced to reckon with what's going on here. So B1 and B2 are closed subspaces. B1 and B2 0. Okay. And for all u in B, there exists ui in Bi such that u is equal to u1 plus u2. Okay, so this is really what it means. But this is equivalent to saying there exists a projector. So I'm always going to write projectors in this format. So this is the range of the projector and this is the kernel of the projector, right? Range and kernel. So B2, that maps B to B boundedly. This is a bounded map. And P, and what it means for it to be a projector is that P of B1, B2 squared is P of B1, B2. Okay, so it's an idempotent. And P B1, B2, B is equal to B1, and the kernel of P B1, B2 is equal to B2. Okay, so maybe I'll erase range and kernel there because I've specified it here. So all of these things are equivalent, and I really want to just talk about this in this very abstract level. I think I've gone off the screen a bit. I want to talk about this at this very abstract level because I want to really emphasize that this has nothing to do with Hilbert spaces, and in fact, in what is to follow, what's also important is that we can talk about splittings in Hilbert spaces that are not orthogonal. That's what's going to really be, the thing that's going to make all of this work in the end. All right. So let me now give you a lemma on all of this, and I'm gonna stick with maybe Banach spaces. But you can, I'll leave it ambiguous, but you certainly don't need any Hilbert space structure here. So let's suppose we have a space X, a Banach space X, that splits into Y plus a Z and Y prime plus a Z prime, with Y contained in a Z prime and Y prime contained in a Z. Okay, so this thing is sitting in here, and this thing is sitting in here. Then we conclude that X is equal to Z intersect Z prime plus Y prime. Okay, that's the conclusion I want to draw. So I hope you can somehow see where we're going with this in terms of the Hodge theorem that I wrote down before. So how do we prove this? So let's first take an X in X. So we can write X as equal to PYZX plus PZYX. Okay? So we can write it as a portion coming from Y and a portion coming from Z. So I'm going to use these projectors because that makes it easier. Now I'm going to simply, now I'm going to just continue. Well, actually maybe I should move this to the next line because I'm going to need a bit of space. So that you can't do on a blackboard, although I still prefer blackboards. So Y prime Z prime PYZX. Okay, so now I'm just going to split along. I'm going to split each of these along this piece here, right? PZ prime Y prime PYZX. And then I'm going to do the same with the other piece, right? So P Y prime Z prime PZYX plus PZ prime Y prime PZYX. Okay, so now what happens? So this part here, okay, so Y prime, this part here, so I'm already in Y, and the projector is an idempotent. If I'm already in the subspace Y, this thing is just going to be equal to PYZ. And this thing is now so this thing is so this piece is now in PYZ. So this is PYZX, okay? And now I have Similar thing here where, oh no, I don't have, yeah. So this part here is now going to be in P, Z, Y, X. Okay, because Y prime is in Z. Okay, so these two things here, they sum up to X again. Yes, they sum up to X. But that's not what I want. I want to, no, hang on. What is going on here? No, this is not what we want. This is not what we want. Sorry. So this thing is going to sum up to P, Y, Z of X. Okay. And now we're going to have a portion here and here. If I combine this and this, I'll end up with a piece here in, so the Y prime, Z prime, Y, Z, and Z, Y. So this is going to give me P, Y prime, Z prime in X, right? So these are the two red pieces. So these are the two red pieces that's going to contribute to that. And now I have again Z, and then I have this piece coming from here. So I have the Y prime Z, and then I now have this remaining piece, right? So P Z prime Y prime, P Z Y X. Now so this thing is in Z prime, this thing is in Y, and this thing is in Y prime. So the only question is why so the only question is why this is in the intersection. Okay, so for that, if we just rerun the proof, so rerun with Y and Y prime interchanged, and if we do that, I mean, we can just read it off from here with Y prime and Z prime interchanged. Okay, so if we do that, we get a Z here, Z there, Z prime, Y prime, we get Y prime here, Z prime, and we get Y and Z. So it tells us that this thing here, so it tells us that P Z prime, Y prime, P Z Y is of X is equal to P Z Y, P Z prime Y prime of X. So that means that this piece so this piece, the yellow piece, is in Z intersect Z prime. Okay, that's what it tells us. So together, what we've proven is that X is a subspace of Y prime plus Y plus Z prime intersect Z. Okay, so I'm putting pluses here because I haven't shown that the intersections of all of these subspaces are mutually empty. But that follows, right? That's clear. So so clearly Z prime intersect Z intersect Y, because Z and Y are empty, right? Z and Y, the intersection would be 0. This is 0. We also have that Z intersect Z prime intersect, Z intersect Y prime is also 0 because Z prime intersect Y prime is 0. And last but not least, Y prime intersect Y is contained in Y prime intersect Z prime, because remember Y here was assumed to be a subspace of Z prime. Okay, so this is of course 0. So if we put all of these things together, that tells us that that tells us that we can upgrade this to sums of this form. So it is there's 0 subspaces, and of course all of these subspaces are contained in X. So that gives us the proof. Okay, that tells us that we can decompose in this way. Okay. Yeah. there is a little bit more. Okay, I'll leave it as an exercise. So there is a little bit more to do. So you want to maybe prove that y prime plus y intersect z prime intersect z is 0. So I'll leave this as an exercise. So actually I should move this to here just to be a bit precise. Let me say that. Yeah, let me put this here and say, oops, didn't work. So let me put this here. That I'll leave as an exercise. And together it follows, this follows. Okay. But I won't labor the point too much. Now, I want to just come back to the proposition, right? So remember the proposition. So maybe I'll just copy and paste the proposition directly. So just so we have it with us here. Okay, so this was the proposition. So now we can just apply the lemma, right? So we set x equal to h. We set z equal to the kernel of gamma. We set z prime equal to the kernel of gamma star. Y equal to the range of gamma star, closure. And y prime equal to the range of gamma, closure. Okay, so now by nilpotency we have that y prime is contained in z, and we have y is contained in z prime. Okay, also we need to know that the spaces sum up. So a fact about, of course, operators is that h is equal to the kernel of this plus the range of gamma star, closure. And it's again the kernel of gamma star plus the range of gamma star star, but that's oops, that's not gamma star. That's back to gamma. So we have this splitting. So then by lemma, conclusion follows. Okay, so again, remarkably, all we have here to make it all work is simply nilpotency. And nilpotency is enough to make everything work, which is, to me, it's just like magic. Okay, now let me rally on. So we have the Hodge decomposition here, but it still doesn't guarantee to us the operators that we want to play with, namely the operator gamma or pi, is a nice operator. But remarkably, this is enough to give us this this following proposition. Is densely defined, right? That's quite remarkable. We can't identify the domain. But we can assert that it's actually a densely defined operator. So the key here really is to exploit this Hodge decomposition. So let's just be motivated by this, and because we have projections here along all of this, these are bounded projections, we can look at the kernel here, and this kernel we know from the proposition that we had before is the kernel of pi. Okay, it's the intersection kernel. So this is really the kernel of pi. So there's nothing to do here, right? So we can look at each piece separately. So the kernel of pi is equal to the kernel of gamma intersect kernel of. So okay, let me maybe before writing this, let me just say what I want to do. So we try to show, what we want to show is that for a u in H, which can be decomposed into u0 plus u1 plus u2, there exists, so via Hodge, right? So via Hodge. So u0 is in the kernel of pi, this is in the range of gamma, and this is in the range of gamma star, closure. That there exist u I K. So the sequence is in K in domain of this such that UI K converges to UI. Okay, in L2 or in H. Okay, so this is what we want to show. So we can look at each piece separately. So let me look at the piece kernel of this, which is equal to the kernel of gamma intersect the kernel of gamma star. There's nothing to do here because this is already contained in the domain of pi. Okay, there's nothing to do with that operator. So instead, let's now look at the second part. So let say V be in the range of this gamma closure. Okay, so that's good. So we want to prove for that. So this is really U1 that I'm calling V. So now we have that gamma star is a densely defined operator from before. So at least in the domain of gamma star, we have something that converges to V. So we have some Vn, or I should call it Vk maybe, Vk in the domain of this gamma star, such that Vk converges to V in H. Okay, that's because gamma star is a densely defined operator, which we know. So now, and also recall, I just want to recall again, I know I wrote this in the last page, I don't want to labor the point, but that H splits into the kernel of gamma plus the range of gamma star closure. Okay, so the other way. Sorry. I want the gamma here and I want the gamma star here. Okay. So I'm gonna now just forcibly. So let me just keep this on here so we can see what we're doing. I'm gonna let Wn be equal to the projection along the I'm going to let this be the projection along the range of to the range of gamma along the kernel of gamma star of Vn. Okay, or I called Vk before. Okay, so let me allow that to be this sequence. Now, clearly, Wk is going to converge to, because this is a bounded map, it's going to converge to the projection of range of gamma closure, kernel of gamma star, V. Okay, so that's what it converges to. But we started with V already in the range of this. So this is equal to V itself. Okay, so projecting firstly to this range here doesn't change anything. It allows us to just get back to the original thing, possibly by a different sequence. Okay. Now what do we have here? So now the thing is that Wk is equal to P. I know I'm writing this again and again. What we have is this. So let me copy this here and paste it. So we have Wk is equal to this, but this projection is 1 minus the projection to the kernel of gamma star along the range of gamma closure Vk. Okay, this is what we have. Now, this is now going to be, so this is in the domain, so this projection, this part is going to obviously be in the domain of, let me draw it. So this projection, this is going to be in the domain of gamma star because it's already in the kernel. And VK, we started with VK already being in we started with this already being in the domain of the gamma star. So together, these two things are guaranteed to be in the domain of gamma star. Okay? So you're asking me, where am I going with this? But the WK is in the range of this gamma closure, which is in the kernel of this gamma, which is in the domain of this gamma. So that means that the WK is in the domain, the intersection domains of these two, dom gamma star intersect dom gamma, which is equal to dom pi as promised. Okay? Now you do this similarly, you do a similar argument, right? So so you do this similarly, interchanging roles, obtain I don't know, WK tilde in dom pi such that WK tilde converges to V tilde for all given V tilde in the range of this gamma star closure. Okay, so each of these pieces can be broken up. So then you can just take the sum of these different sequences, use the fact that the norm splits, right? So the algorithm is for u in H, u equals u0 plus u1 plus u2, and then because these things are projections, the norm of u is comparable to u0 plus u1 plus u2, right? And so what you do is you just use these separate sequences and set up u1k which converges to this and u2k which converges to this, and for this you don't need to do anything. Okay, so that's the proof to show quite remarkably that the domain of this operator, even if we can't identify it, if we don't have nice things here, we can still show that this is a densely defined operator. Now, so this is good. This is not so good. My pen's gone dead. Let me just. Okay, so this is good because the consequence of this. So what this leads to is that this exists as pi is densely defined. Okay? And of course the domain of this pi is just simply given as V in H such that pi u V is bounded by u. Okay, that's the domain. Now I'm gonna tell you something. I would love to have had the opportunity to prove it, but I think in the interest of time, I'll skip it. But the bottom line is that actually this is self-adjoint. Okay, so similarly, again, using nilpotency, using the things that we've just constructed, and really using nilpotency again, allows us, so i.e., that the domain of this pi star, so what we need to prove is that the domain of this is equal to the original domain. Okay, or I should really say that this direction is the interesting direction because it's a symmetric operator. Because it's a symmetric operator, we'll always have that the domain of the adjoint contains the domain of this. But what's interesting is this direction. I won't prove it in the interest of time. But I just want to really emphasize this because this is fundamental. Okay, so again, nilpotency, Hodge, and just using the techniques that we've developed now to really just compute the domain of this again to get to the right places via nilpotency. So before time gets the better of us, I want to have an interlude back to reality. Okay, so what have we been able to do so far? So let's have M compact, no boundary, and I want G to be just a rough Riemannian metric. So measurable coefficient, you know, yeah, and this gives us, of course, a metric on forms and tensors. And we have L2 theory of all of this with respect to G. So this is, psi is in this L2 if and only if the integral of Gx, psi x, d mu Gx is finite. Okay, that's the norm, the norm squared of the inner product. Okay. So by a local argument, by localization, and using the fact that star d of m is the Rn star inside a chart, we get that D closed is densely defined, closed, and nilpotent, right? And that then gives us that D star of G is densely defined, closed, and nilpotent. So if we now take dg and just sum these operators together, this is guaranteed now to be a densely defined, closed, and in fact self-adjoint operator. Okay, we don't have elliptic regularity. We don't know what the domain of this operator is. We cannot, in general, identify it. It's really, really bad, as we saw, because we can construct, by example, that smooth functions won't even be, or smooth sections, I should say, smooth sections won't necessarily be in the domain of this operator. Nevertheless, the question that we asked, at least, kernel of dg star, dg, not dg star, being isomorphic to the singular cohomology, this is at least well posed now. Okay, this is at least a question that we can ask. So, an interesting question to ask is, how do we possibly do this, right? What might be a strategy that allows us to get to this? And I want to just give a sort of a rudimentary calculation. So how would we attack this? Okay. So let's think about what the original Hodge theorem says, right? So if we have H and H prime smooth, then the original Hodge theorem tells us that the kernel of DH is isomorphic to the singular cohomology. Okay, I won't bother putting the restrictions to the K-forms. It's certainly true, but let's just put this. And also that the kernel of DH prime is isomorphic to H singular. So that tells us, actually, a posteriori, that the kernels of these operators are isomorphic to each other. We can factor through this isomorphism to get to that. So, okay. So what could we possibly do in our situation? Well, fix our G, which is an RRM. Okay. So that means that for all x in M, there exists a chart psi u, and a constant which depends on u greater than or equal to 1, such that, and this of course holds even for the non-compact setting, right? But here compactness, such that the pullback of the Euclidean norm inside this chart holds for y almost everywhere in U. But M compact means that we have a finite collection, right? We can cover by finitely many. Okay, so there's a finite cover by such locally comparable charts. And if we choose a smooth partition of unity subordinate to, let me call this C, and then we can just define G tilde as just the metric that we get by pulling back these things, right? Eta I, psi I, pullback of the Euclidean metric, and this is guaranteed now to be a smooth metric, right? Now, the bottom line is that we can, of course, choose, so there's finite number of charts, which means there's finite number of constants. So there exists a C tilde, and this C could be very large. It's not like somehow we can control what this C looks like when we shrink. So what I'm really setting up here is a large perturbation problem. So we have some C greater than or equal to 1, such that C tilde U G tilde, so C tilde inverse, less than or equal to U G less than or equal to C tilde of U G tilde, X almost everywhere in, well, there's no X here, so I'll say almost everywhere in M. So on all of them, we've got a global comparability, right? So that's pretty good. And because G is a smooth metric, for any smooth metric G infinity, we have that G tilde is comparable to G infinity in this sense, right? In this sense. So there's some constant that allows us to bound it above and below. Again, it just comes down to compactness. But that tells us that the L2 norm, in fact, it's true for LP, but in particular for L2 norm of forms with respect to G is comparable to the L2 norm with respect to any smooth metric, right? For any G infinity smooth. So we're done. We can get to a Hodge theorem if we can prove. So can we prove, and we can, but can we prove, so let me ask the question, that the kernel of dg is now isomorphic to the kernel of dg infinity, right? Because this thing, this is smooth. This object is smooth. So this is isomorphic to H star singular of M, right? And then we would answer our original question in the affirmative. So the key here, so what is really a concept? So the key here is this, right? So let me maybe put that in red, right? So this is the key. So in the original Hodge theorem, what is a consequence of proving the Hodge theorem by smooth methods? We want to really make this the first class object of study for us here, because then we can tether through the smooth Hodge theory to try and get to a non-smooth Hodge theory in our case. Okay? So this is somehow the goal of what we want to really do. I think I started a little later, so if you don't mind, maybe I'll just go a little bit more and start on some of the things that we want to talk about. So really what we want to do is to set up an abstract version of this problem. Okay, so that it's applicable. The reason I'm showing you all of this, it goes back to the question that was asked in the last seminar when I was talking what happens in non-smooth situations, what happens if the manifold is non-smooth, etc., etc. So I want to really give you the abstract theory, because then if you are working on some interesting problems where you need something which lifts away from all of these specifics, you have a framework to think in. Yeah, okay. So let me start a new section, which I'll continue on Friday. So I want to say back to the abstract picture. Okay, so change of metrics. So that's what I want to get back to. So now I'm going to fix my set, and I'm going to consider two inner products. So 1 and 2. Okay, we saw in the last picture, in the specific situation, that what we get are inner products. So these are Hilbert spaces, which are Banach space isomorphic. With this norm comparable to this norm, right? That's the picture that I want to live in. Now, Rie's representation theorem very kindly gives us a bounded operator and positive. Okay, so the spectrum of the operator is in the real part, so and I should say self-adjoint. Such that I can write the second inner product in terms of the first. Okay, so this is via Rie's rep. Okay, and I want to make a remark that if gamma is an operator gamma is closed and densely defined and nilpotent with respect to 1 if and only if it is with respect to 2. Okay, so the gamma doesn't change. Now, in our specific situation where we're looking at a manifold, D is related to the differentiable structure. So the metric doesn't affect D. It's really the D star which is affected, right? However, so I want to say however, this of 1 and gamma star of 2 are the objects that are different. So in some sense, this contains the topology, this contains the geometry, right? That's broadly speaking a way to see it. So the geometry is really seen by the adjoint. Now, I've used what I'm going to prove a number of times loosely, but I want to really pin it down here in this abstract setting. So what I want to say is that the gamma star of 2 is equal to B inverse gamma star of 1B. Okay? And the domain of gamma star of 2 is B inverse domain of gamma star of 1. Okay? So let me at least go through this proof before stopping. So so let's take a U. I just want to give you a feel for how to prove this. So let me take a U in this. So that means that gamma star 2 U V is equal to U gamma of V for all V in dom gamma. Okay. And so now, with respect to the inner product 2. This is with respect to inner product 2, right? We're computing the adjoint here with respect to the inner product 2. And Rie's representation gives me this B, so I can chuck in a B here. So BU gamma V2 for all V in dom gamma. Now, this means that because I've got this in adjoint form, this tells me that BU is in DOM, gamma star, sorry, there's not a 2 here, I'm sorry. This is a 1. Okay, so this is with respect to 1. But I want to know now that the BU is in gamma star 1. So this gives me that because I have a comparable inner product here. So if I apply representation and compute the domain of the adjoint and so on and so forth with respect to this, I'm all good. So that means that I can now just pull this across, gamma star 1, BU, V, with respect to 1. And now I want to change it back to 2. So I'm going to put a B inverse gamma star 1 BUV. Okay, 1. And of course you can go back the other way. So other way, exercise. So you can go back the other way. So at least this tells us. So this tells us that. What does this tell us? This tells us that gamma star 2 is contained in B inverse gamma star 1B. Okay, so this means that the domains are contained and they act the same. And the other direction is an exercise. Okay? So we can see now the way to describe these operators. B can be really thought of as something like a global coordinate system. So that's really, really nice. Okay. So what we have here is the following corollary, that now the range of this 2 is equal to B inverse, well, I'll put a closure on here, range of gamma star 1, and the kernel of gamma star 2 is equal to B inverse the kernel of gamma star 1. So that means that H is equal to, by Hodge, if we apply Hodge now to the operator gamma 2, we get that this is the kernel of gamma star 1, kernel of gamma intersect the kernel of gamma star 1 with a B inverse in front of it, plus the range of gamma closure plus B inverse the range of gamma star 1 closure. Okay, and remember we also have, so this is applying Hodge to gamma plus gamma star 2. Okay, now if we apply Hodge to the original one, we get that this is kernel of gamma intersect the kernel of gamma star 1 plus the range of gamma plus now the range of gamma star 1 closure. Okay, so in some sense what's really happening here, so I should really also point out that this is the kernel of pi 2, this is the kernel of pi 1. Okay, so and I'm not writing, so it is true that if we compute this with respect to the one inner product, these are orthogonal sums, but in general we've got two inner products floating around now, which makes it more like a Banach space problem than really a Hilbert space problem. So that's why I don't want to put orthogonal complements and stuff here, because we have two inner products floating around. So we still have projections. They're bounded projections, and that's all we care about. Okay. Now, what we will do next time, and what we want to really see, is that from this point of view, the problem reduces to asserting that the kernel of pi 2 is isomorphic to the kernel of pi 1. Okay? And we will think about a way to do it, and I'll give a helpful lemma that allows us to essentially make this calculation, but I think I have sort of overstayed my welcome a bit and spoken a bit longer, so maybe I'll leave it at this and just let you kind of stew over some of these things and yeah, open the floor to questions.